Hey, welcome in everybody. For right now, go ahead and start the warm-up. And I'll take attendance in about 2 minutes and we'll get going once everybody's here or not. Today, we are gonna have time to work on the section 4 stuff. And I'm also gonna do the review and breakdown of what you guys will need for the chapter test, which is next week on Friday after all of the AP stuff is done and out of the way. I'm also going to say a little bit of stuff today about like the types of sums that we can't take and kind of logically how they should behave. And I'm going to say one thing, which is obviously not going to be on the test because it's like a topic from college level mathematics on all this stuff. But I think it is extremely interesting. Yeah, that is to say there is a way that we can take one of our sums that can't be taken, and if you do it, you get a really interesting result. But yeah, in the meantime, go ahead and take a look at this warm-up here. I have one poorly defined sequence. I'm telling you that A is equal to 3, 9/2, da-da-da-da-da-da-da-da. And for this sequence, I'm only giving you the first 2 values so that exactly what builds this sequence is ambiguous. It is not enough information to build an equation out of 2 points. You can't do that. It's literally impossible. You either need 3 points to fix the behavior of a function, or you need to know what type of function it is outright. So item number 1, assuming that these first 2 points are generated arithmetically, find the series for the first 20 terms. And then item number 2, find the series for this if it happens to be produced geometrically. So for both of these types of structures, figure out what the explicit series equation should be, and then calculate what that series is over the first 20 values. Now, like obviously, which one of these should be bigger? Which one of these should produce a bigger answer before we do any calculation at all? Is anybody out there? Hello? Yeah, I see my mic bobbing.
Hey, Mr. Robinson.
Hello, you can hear me, right?
Yeah.
Yeah, we can hear you.
Okay. Which one of these should produce a bigger sum? These numbers growing arithmetically or these numbers growing geometrically?
Geometrically.
Obviously, geometrically. That is to say, an exponential equation should grow way quicker than a linear one. So one good indicator to know that you have done this task correctly is that your solution to part 2 should be much bigger than your solution to part A. Like I said, go through, figure it out. And then today we're going to do some like wrap-up notes on section 4. You already have everything you need to solve all of the questions in section 4. I just want to talk about a little bit of logic for the sums that we cannot actually take. What AP tests do you guys have on Friday? How come we have the next 2 days off?
U.S. history.
Oh, word. Yeah, that's right. Yeah, U.S. history. That's a fun one. How are you guys feeling for that? If you don't want to talk, use the like the little emote options that they have in Zoom. give me a thumbs up or some other weird little emojis that can pop up over your name. Oh, I got a thumbs up. Tight. Tight. Oh, hey, lots of thumbs up. Weird. Oh, claps. Neato. That's good. Yeah, let me take attendance and then we'll get rolling.
Mr. Robinson?
Yep.
Do you want us to turn in our classwork today?
Nah, since it's just like 2 days, we'll just roll it into next week. So next week, the assignment that'll go up will say week 8 and 9 classwork. And then instead of giving 10 points for it, I'll give 14 points for it.
Okay.
Yeah, we'll save ourselves an upload, and I'll save myself a bunch of space inside of my Google Drive. I'm finally getting California license plates on my car. It took 3 months to do the paperwork, but it's finally come through, which is what I had to deal with yesterday. And then this afternoon, I have a final because it's finals week at Cal State LA.
Wait, you just got the plates?
Yeah. There was a bunch of complicated paperwork involved with inheriting a car and then bringing it over state lines.
So, Mr. Robinson, you have to register the car to California?
Yeah, that's part of it. The other part that made the thing complicated was that I needed to transfer the title over, and I had to both change the name on the pink slip and bring it over state lines, which I thought I could do all at once. You have to do it as 2 steps, and the fact that you have to do it as 2 steps is part of what like slowed me down in the process so much. But yeah, like whatever state a car is in, it needs to have those plates, though you see a bunch of people ignoring that. Like there's a dude who lives in my building who's had Texas plates here for the last 3 years, and he definitely is here all the time. He like isn't going back and forth between here and Texas. Don't get me wrong, I would never narc though. It's like none of my business. I just don't want like any trouble should I happen to be pulled over. Okay, cool. I guess that's it. Okay, let's go ahead and get started. So item number 1, how do we do this if this guy here is going to be arithmetic? What would the general equation be? I'm sorry, what would the explicit equation be for this particular sequence?
It shouldn't be the common difference multiplied by or the common difference times n plus b.
Correct. So what is the common difference? How much am I adding to go from 3 to 9/2?
Three over 2?
Oh, we have 1/1.5.
Yeah, so here we're going from 3 to what would that be, 4.5, right? So from here to here, we're adding 1.5. So that is to say my common difference is 1.5 times n plus b. And in order to make this work out, we need to have the correct value for b. So I'm going to plug in one of our known values. 3 is going to be equal to 3/2 times 1 plus b, where all I'm doing here is I'm plugging in the first value, and along with that, plugging in the fact that n is equal to 1. And so 3 minus 3/2, or 3 minus 1.5, is also just 1.5. So b is equal to 3/2 also. So this is to say that if this thing were an arithmetic sequence, if that were what's giving us these first 2 values, that's just 3/2n plus 3/2. This is the linear equation which is generating this sequence. And so if we want to add this over the first 20 values, we can do that very quickly by using the series equation for an arithmetic sequence, which is to say s sub n is equal to n/2 multiplied by a1 plus an, right? So the first and the last number in the arithmetic sequence multiplied by the number of pairs over 2, because just like with the counting numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, or whatever, that classic example where we add up all the digits between 1 and 100, the first and the last digit make a sum of 101, and then we have a certain number of pairs, because as you move in, right, 1 plus 100 gives us 101, 2 plus 99 gives us 101, 3 plus 98 gives us 101, blah, 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 all the way down. And so in order to do this sum, well, we're summing the first 20 terms. So S sub 20 is going to be equal to 20 over 2, which is to say that we're going to produce 10 pairs of numbers here which have equal values. And to figure out the value of all of these pairs, it's just the first number, 3, plus whatever the 20th number would be. So what do you get if you plug in 20 to the sequence generator?
12 and 1/3, or it should be 37 over 3.
I don't think you can land on a third if we're counting by halves.
Isn't it 63 over 2 or something like that?
Wait,
That sounds correct, yeah. So it should be 3 over 2 times 20 plus quantity 3 over 2.
oh
And
yeah,
then we'll hit it with the frac. So 63 over 2. So this is 3 plus 63 over 2. And then we just perform this tabulation, you know. So I'll take this guy, 63 over 2, I'll add to this 3. So that means that of our 10 pairs, each one of our pairs is going to sum to 34.5. And then I'll multiply this by 10. And so the sum of the first 20 digits here should be equal to 345. And that is if the thing that generated those first 2 points is actually growing arithmetically. Is that okay for case 1 or problem 1? Yeah?
Yeah.
Okay.
yep.
And then item 2 here, if this is geometric. So if this is geometric, what is my ratio? What would you have to multiply to go from 3 to 9 over 2?
Isn't
3
it
over
also 3 over 2?
Yeah, the common ratio here would be 3 over 2, but this means that if we're doing this by multiplication, then instead of adding by 3 over 2 every time, we're actually multiplying by 3 over 2 every time. So this is to say, and you know, it's so weird. This math is easier because it's arithmetic, but because of the structures that we have to conform to in order to calculate the sums, there's a lot more like steps to do here on the left. Here on the right, a sub n is just going to be equal to our first number multiplied by the common ratio, 3 over 2 to the n minus 1. That's it. That's the whole sequence generator. That's all we need to know. And then if I want the sum, then S sub n is going to be equal to what for our geometric series? It's that first term multiplied by
1 minus r to the n.
all divided by
1 minus r.
Very good. And again, I think one of the most elegant things in this whole textbook that isn't the trigonometric identity stuff is the derivation of that relationship. If you don't remember how to do it, take a look at it. It's real easy to memorize if you remember what the steps are. Write out formally what the series would constitute for a geometric series. So that would be a1 plus a1r plus a1r squared plus a1r cubed all the way down. Take both sides of that equation, multiply by r, subtract them, and factor, and you can show very quickly that the sum of any geometric series must be this by fancy manipulation. And so S sub 20 is going to be equal to our first term, 3 times 1 minus 3 over 2 raised to the 20th power, then divided by 1 minus 3 over 2. And so, you know, this should give us the same thing as if we were to add up the first 20 digits of this. So it'll be 3 times 1 minus quantity 3 over 2. Then I'll raise the stuff in that parentheses to the 20th power. And then it's going to be that number divided by 1 minus quantity 3 over 2. I made a mistake somewhere.
Robinson, shouldn't the exponent, shouldn't n be inside the parentheses? Just
That
on
is
the-
right. It's just on R. Yep. That's what the problem is. Thank you. So this is actually, the words were correct. I wrote it down wrong. The n is there. So the 20th is there, and we get a very, very different solution, all for the sake of the position of a parenthesis. So this is actually 3 times 1 minus quantity 3 over 2. This guy is raised to the 20th power, and then I'll close the parenthesis on that. So that's the correct numerator. And then we take, oh heck, minus, and then we take this and divide it by 1 minus quantity 3 over 2. Oh my God, my fingers today. Cool. I'm so glad that this final that I have this afternoon isn't going to have any numbers on it, because I seem to be all butterfingers with my calculator right now. Nonetheless, if we were to take this and we were to sum it up, of course, this could be cleanly expressed as some fraction. It's probably too complicated for this calculator to do it. Yeah, it's too nasty for this calculator to do it. But the sum of the first 20 digits here is 19,945.54038. Much bigger than if these 2 points were just growing arithmetically. Are there any questions on today's warm-up? Is this okay?
Yep.
Okay. Now, some final thoughts on section 4, just because, you know, I always feel like this section is treated really like ham-handedly in pre-cal, but there's a lot of subtlety here. So the last thing that I want to talk about real quick is just a little bit of like logic in terms of why it is that we're not taking the series that we're not taking. So here are the series that we can take. So there are effectively 3 different series that we are allowed to take right now with what we have. We can take a finite arithmetic series. We can take a finite geometric series. And we can take an infinite geometric series. But we have a condition on the taking of this infinite geometric series. That is that we are only allowed to take the infinite geometric series so long as the series itself converges. Yeah. And for these 3 cases, we have different formulations that are derived by 2 different means. For our finite arithmetic series, S sub n is equal to some number of pairs multiplied by the value of each pair. Very nifty trick if you ever have to add up a lot of numbers. We have a finite geometric series, which is derived by even cleverer means. Some stuff figured out for us by the ancient Greeks. A sub 1 times 1 minus r to the n, then divided by 1 minus r. And in the case that r to the n disappears nicely as you go to bigger and bigger and bigger and bigger n values, we can also do this for an infinite geometric series, which we didn't do in the warm-up today. But this is the same equation, except with the r to the n struck out of it. So that is to say that S sub infinity for a particular family of geometric series is just the first term divided by 1 minus r. And we saw a bunch of justification, and then there's that nifty diagram that I showed you guys. However, let's talk briefly about series that we can't take and why. And some of these are obvious and some of these are not obvious. And I have one extra wrinkle that I'm going to add to all of this to mess up your guys' days in case I can convince some of you to maybe major in math, or honestly, minoring in math is a strong choice. If you were going to head into some sort of technical field anyway, like if you were going to happen to major in physics the way that I did, or major in engineering, or major in one of the other hard sciences, usually taking a hard science requires so much mathematics that you get most of the way to getting a minor in mathematics. If you have a major that is in some sort of technical field and you have a little bit of time in your college schedule, consider minoring in math. I really regret not minoring in math at UCLA. I probably only would have needed like 2 extra courses. Anyway, here are some series that we can't take. Basically all of the categories aside from these 3 narrow ones. So that is to say that we can't take infinite arithmetic series, You cannot take an infinite arithmetic series. You also cannot take infinite geometric series which are not converging. So let's talk real quick about the notion of an infinite arithmetic series. What do you think you would get if you attempted to sit down and tabulate an infinite arithmetic series? Like, if I were to actually try and take the actual sum of starting from 1 up to infinity of a linear equation, where our linear equation is just going to be the same that we had before. So our common difference, d, multiplied by n, plus some constant b. Like, where do you think this goes?
Just a straight line that goes on forever, I guess.
So that's what it would be if you were to graph it. But what if you were to then take all of the output values, all of the y's, and you were to try and add them up? What do you think it's going to trend to? If you take 1 and add it to 2 and add it to 3 and add it to 4 and add it to 5 and add it to 6 and do that all the way until infinity, what do you think you get for the sum?
Infinity.
That is correct. Hold on, let me close the door. I think my wife just started remembering me. I only had the door open because my cat was outside screaming at me to open the door. And I always do what the cats say. Hey, those of you cat owners out there, always do what your cat says. They're in charge. Yeah, it'll trend to infinity. So if you take numbers and you keep adding them and adding them and adding them and adding them, the sum will get bigger and bigger and bigger and bigger, and you are going to trend towards infinity. Now, since infinity is not actually a number, we cannot say that this equals infinity, but here's my quick notes on this. So if d is greater than 0, which is just a fancy way of saying that if our common difference is positive, right, if we're adding numbers, then that means that s sub infinity in this case would trend to infinity. And then if this is a negative common difference, right, if our sequence was 5, 4, 3, 2, 1, 0, negative 1, negative 2, negative 3, negative 4, negative 5, what do you think that would trend towards? And I'll actually be cool, and instead of using the word infinity, I'll just use the symbol. So if the common difference is positive, it'll trend to positive infinity. But if the difference is negative,
Negative infinity.
yeah, then s sub infinity will trend to negative infinity. Is that okay? That's all I have to say on that. So if the numbers keep getting bigger and you keep adding them together, it's going to take you up to positive infinity. If the numbers keep getting bigger in the negative direction and you add up all of those negative numbers, we have some notion of negative infinity, an infinitely large number that just happens to have a negative magnitude. And now what's even more problematic, you think this is about to be problematic. We're going to come back to this. So if you have colors out there, let me go ahead and put a fat asterisk on this idea, which I'm about to ruin for you forever. And I don't know, if you listen very carefully, maybe it'll win you $1 million in a few years down the road, if I happen to be teaching a math genius. Okay, we'll come back to this on the next page. Next page, we'll start with a red asterisk. Over here, top right, an infinite geometric series which is not converging. So this is to say, if we were to be asked to take the sum of some infinite geometric series from n is equal to 1 all the way up until infinity, where this is our first term, a sub 1, times our common ratio raised to the n minus 1, except we have the case that r is not in our convergent set. So here, this guy only works in the very specific limit that r falls between what two magic numbers?
0 and 1.
Exactly. It has to be some fraction which is less than 1, so that every time we multiply and then add, the next number that we're adding gets smaller and smaller and smaller and smaller and smaller and smaller and smaller, and it shrinks away so quickly that future numbers cease to affect the sum. So let's go ahead and say that we have some sort of infinite geometric series that is not converging. And our first case that we want to consider is if R is outside of that limitation, but to the right. So R is greater than 1. So what do you think you would get in an infinite geometric series if we were to add up 2, 4, 6, 8, 16, 32, 64, 128, 256? What do you get if you add up all of those?
Infinity, like literally.
Right. Yeah, same as before. So S of
Yeah.
infinity will trend to infinity as well. And here's the wacky thing. This is why at the top of this section, I talked about different types of infinity, which is not an idea that you're going to be exposed to or that you need to worry about until you guys are in your junior or senior year of college and you happen to be studying like math for the sake of analysis. These are two different types of infinity. Both of these functions will trend to infinity with their sum, right? However, this one is uncountably large, while this one tends to be countably large. You can't really make smart manipulations or statements about this generally. However, I'm going to show you guys on our next page that people have done some work with this particular countable infinity here on the left. And now here's what's even wilder. What happens if R is less than 1? So what if you are doing some sort of summation where you have a negative common ratio? What happens to the numbers when you do a geometric sequence with a negative R? What's true of the signs?
Each, like, it flips from negative to positive each n value for each n.
Yeah, exactly. So with each step that we take, right, because a negative number raised to an even power will give us back a positive number. Negative 2 squared is positive 4. But a negative number raised to an odd power gives us back a negative number. That is to say, negative 2 cubed gives us back negative 8. So as we head along through our values here, and I think it's easiest to capture this as a quick little graph, as we step forward through our numbers, the first number that we're going to add to our sum is going to be positive. The first number that we're going to add to our sum is going to, or the next number that we add to our sum will be negative. The next number that we add to our sum will be positive. The next number that we add to our sum will be negative. The next number that we add to our sum will be positive. Back, forth, back, forth, back, forth, back, forth. So we have this flip-flopping of signs, positive, negative, positive, negative, positive, negative. And every time you take a step forward, that next number is going to be radically larger than your previous number. And in a lot of cases, it can actually be bigger than the entire sum itself. So by the time you're here, you might be at a sum of positive 10, and then find out that your next number is negative 64, which suddenly swings the whole sum from a positive sum to a negative sum. What do you think this trends to?
Positive and negative infinity.
So it can't do both. It definitely can't do both. So we have a notion that, well, okay, it might trend to positive infinity or it might trend to negative infinity. And that actually depends on whether or not infinity is positive or negative. That's not a question, or yeah, that's not a question you can ask of infinity. We also have a notion that, like, what if all the positives and negatives, what if they all cancel out over the long run? Then what would it trend to? If you had all of the positives and negatives cancel out, what would it trend to? What do you think? There's also an argument that this thing might trend to 0. That if the effects of adding up all of these big positives and all of these big negatives, what if they like kind of smooth out in the long run and it trends to 0? So there's a valid argument to be made that this thing trends to infinity. There's a good argument to be made that it trends to negative infinity. And there's also a good argument to be made that it might even trend to 0. You can't know. So we have no idea. There is no statement about the sum.
Well, that's no fun.
It is very fun if you're in mathematics. This is the kind of stuff worth like really, really digging into. And for limited cases, you might be able to do an analysis on which this is. But if you look back to the notes from section 1, I called this particular orientation of sequence, I said this has a name. This is what it means for something to behave chaotically. Chaotic is a technical term in mathematics, but this thing has a future that we cannot predict based on its current baseline set of equations. And that is precisely what makes this a chaotic system. Is this okay? So I just wanted to say explicitly, like, yo, in terms of this class, I'm only asking you to do these 3 types of sums, and that's not just because this is pre-cal. That's because there's not really anything intelligent you can say about the alternatives. Yeah. Now, this big red asterisk, it turns out, depending on what mathematician you talk to, there is one particular arithmetic sum, one particular infinite arithmetic series that we can take. The following sum is defined, depending on which professor you talk to and probably how old they are. If they're older, they're going to say that what I'm about to write down is false. If they're younger, they're probably going to be a little bit more likely to agree with what I'm about to say. In the case of the particular arithmetic sum, so the infinite sum from n is equal to 1 all the way up to infinity of the sequence generated by n plus 0, which, just to make sure we're all clear here, what is the first digit?
1.
And then the next one would be to add,
So also 1.
1, yeah, so 2.
2, and then the next one,
3.
3, right? So this is literally just the set of instructions to add up the counting numbers, right? To just say, well, the only value is going to be n, the common difference is implicitly 1, and there is no baseline value. So this is just 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10, all the way down. This is well defined as negative 112. And this is not a conjecture or a troll or whatever. There is an entire field of study dedicated to this particular summation series. And more or less in any application where you could correctly use that object on the left, in any case where you would add up all of the numbers from 1 to infinity, if you were to substitute into its place instead the value negative 112, those equations will always fold out and give you back the exact same solution. It has been shown with mathematical certainty that in any case where you could correctly use the sum of all positive integers, that plugging into that position in the equation, negative 112, gives you the exact same sum. Now, how is it that adding up ever increasing numbers, not only does the sum not equal an integer, but it also isn't even positive, right? It gives us back a negative fraction. To understand this argument will take you a few years of study. But this argument is based on the use of the Riemann Zeta function. And the Riemann Zeta function is a nightmare mathematical object. It is such a nightmare that if you solve it explicitly, an explicit solution will win you $1 million. And I mean, past that, it would also probably win you a Fields Medal, which, if you don't know, the Fields Medal is like the Nobel Prize for mathematics, because there is no Nobel Prize for pure mathematics, except it's harder to win than the Nobel Prize because the Nobel Prize goes out every year. The Fields Medal only goes out if the committee thinks that it's deserving. So there are plenty of years with no Fields Medals going out. But yeah, just so y'all know, I'm not going to leave it here. It's just that this is radically outside the scope of the class. So I'll post a link to a YouTube video about the Riemann Zeta function and how it is that, exactly how it is that the sum of all positive integers can give back a negative fraction. Just so you know, I am on board. I believe in this value simply because as a scientist, I only care about solutions to problems that work. And there are a few physical systems which are correctly solved by the use of this substitution. I don't fully understand the total argument about the Riemann Zeta function and how it arrives here, but I have seen it work in the solution of a physical system. Are there any questions here? And then I'll talk about the quiz.
This is just wild stuff. Not really.
Okay.
Mr. Robinson,
Yeah.
for the geometric series that you used on like the other page, you were talking about how you like were adding only the not positive, even numbers. Like, how would that get you to infinity if it's only the even numbers?
Oh, here in the chaotic system?
Yeah, because you were like 2, 4, 6. Like you weren't.
Yeah. So here's how, okay. So my argument is, as you step forward through a geometric series, this number could be so big that it overwhelms the entire preceding sum, right? So like if this is actually growing geometrically, you could get to a case where up until this exact moment, the sum is positive 50. But if my next number is negative 64, then I add that in, it's going to take my whole positive sum and swing it back to the negative side. So not only is the value swinging back and forth, but if r is large enough and negative, then it could swing the entire sum with every single step through n. Is that okay?
Yeah.
So the argument for why it could be one of these infinities is based entirely only on the last number. So if infinity is an even number, right, which is the wrong way to think about infinity, you can't say whether or not it's odd or even. But if it was even, right, then a negative number raised to a very, 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 very big even number would give us back a very, very, very big positive number. So you end up here at positive infinity if infinity is even, which is the wrong question to ask about infinity because that like can't really be known about it. Or the converse would be true down here. If infinity is a negative number and we take is an odd number and we take a negative number, raise it to the power of an odd number, then the final digit would be some huge, overwhelming negative number, and it would swing our entire sum in the negative direction. And this would end up being our sum if infinity is odd. And again, you can't know that about infinity, so you can't know where this sum is going to go.
So like you would have to include odd and even numbers.
When you add this up for a negative r, you would have to add up all the negative and positive numbers, which is what makes it impossible to guess where this is going in the long run.
Oh, okay.
It's just going to swing back and forth, and it depends on some later values that are indeterminable to us.
So Mr. Robinson, with this argument, it's saying that eventually, the switching of signs from positive to negative eventually become equal, because in the
No.
first use, no.
No, the switching signs from positive to negative is something that you can't learn about math. I know up to here, math is very, for some of you, math can be very comforting because like unlike history where you're like, oh, I have to make an argument based on some evidence and there is no correct answer. No. Up until this point in math, there is always a correct answer. Or if there isn't, there's a good reason why there isn't, right? This is not that. This is the part of math where we have to make arguments. I'm saying there's no statement. The answer to this is there is no statement unless you know a lot about the system and you can make some sort of very clever, convenient substitution. There are limited cases where you could learn about this, but in general, there's no one quick and fast rule. Like, if you were to figure this out or whatever and come up with a rule or come up with the equivalent of this, for the case where r is negative, you would win a Fields Medal. You would like be a math professor immediately. Okay, that's good stuff. But yeah, like I said, I'll post a YouTube video to this argument, why it is that this goes to -1/12. I think the video was good. You'll get a flavor for graduate level mathematics. And it also talks a little bit about the $1 million prize offered for explicit solutions to the Riemann Zeta function. In general, the homie who runs this YouTube channel, the channel is called 3 Blue 1 Brown. I would recommend just subscribing, especially since this COVID-19 breakout. The dog who runs it is this really smart dude. He has been doing weekly videos for every level of math. He's doing a pre-cal series. He also has a calculus series dedicated to AP calculus. Really, really high quality stuff. Anyway, next Friday's quiz. And of course, I'll be posting a review assignment today. And next Thursday will be your chance to ask questions about that review assignment or any last minute things of that nature. So for next Friday's quiz, we can move it down. Here's what we need to know about. From 11.1, I'm not really going to be asking that much stuff that is specifically from here, because it's just kind of a mixed bag of different ways that we could generate series and sequences. So basically what I need you to be able to do from it is inspect a sequence. And from this, you need to be able to write two different things for me. So you need to be able to inspect that sequence and then either write an explicit series and also write a recursive sequence. The difference, of course, between these two is that if it's explicit, you could just plug in n and get any value. If you wanted to know the millionth term, it would take no work at all. You just plug in the number 1 million and the equation will give it back to you. Or if it's the recursive sequence, that means that the next number is built off of the previous number. So to get to the 1 millionth sequence or the 1 millionth term would be no fun, because you would have to start at whatever term you had and add or multiply or whatever the step is to generate the rest of the numbers there. If you look back at the notes on section 1, I gave some generalized advice. Look for a common difference, look for a common ratio, analyze numerators and denominators separately, and if the sign is flipping back and forth, back and forth, back and forth, back and forth, there must be a -1 raised to the nth power somewhere in there. I'm going to keep these reasonable. I'm not going to do anything crazy where the correct answer has like built into it decimals or some other nonsense. Following that generalized advice will be able to give you the correct answer. The other thing in here, and this is the weird thing about 11.1, is that this is also where the notion of the factorial is introduced. And we didn't really use it since. And we actually won't be using the factorial that much until the second half of this chapter. But please just realize that the factorial as a mathematical operation is n exclamation mark, which is equal to n times n minus 1 times n minus 2 times n minus 3. And you take this product all the way down until 1. So 10 factorial is 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. This is sometimes necessary to write the explicit sequence for a recursive sequence where what you're doing is taking the previous number and multiplying it by n. Any question that involves a factorial will be very explicit either in the presence of the factorial command or in the request for you to write it as a factorial. I won't just expect you to identify the fact that this thing is a factorial. And then the next two sections are really straightforward, I think. 11.2 and 11.3 are the same notion, except we get really detailed about arithmetic sequences and geometric sequences. And for both of these, I need you to be able to, again, use the common difference and the common ratio in order to write explicit or recursive forms based on 2 data points or based on an example list of numbers, stuff like that. The other thing I'll ask you to do is based on the explicit form to solve for future terms. So the way in which this will mostly be analyzed is I give you like the first 5 digits and then I ask you for what the 1 millionth digit is. Write out the explicit form and then plug in the value that I'm asking you to solve for. And then past this, the other important thing is 11.4 series. And so in this, basically 2 skills: identify which series are calculable, so that is to say, I will feed in a few series equations which cannot be done. So infinite arithmetic series cannot be done. infinite geometric series cannot be done if R is outside of a specific set of boundaries. However, I'm not going to ask for these details. I won't ask you why not. I will simply pose a few questions which are impossible, and you need to identify them as such, right? Is like, oh, this doesn't meet the conditions for us to actually take a series. And then for the ones which work, calculate series using our three relations, where our three relations are these three, the three that I put at the top. So the series that we can take are these three equations here. And the quiz will look very similar to the review assignment that I'm going to post today. Is that stuff good? Is that okay?
Yep, sounds good.
Cool. Yeah.
Mr. when is
Yes. Yeah.
when is it, please?
Next Friday. Yeah, so we have a bunch of days off for all of your guys' AP tests. So after today, I'm not going to ask you to come back here until next Thursday, because y'all have a whole bunch of tests between now and then. And so do I. I have one this afternoon. So next Thursday, we'll meet back up and we'll go over the review assignment. And then the day afterwards, we'll have our quiz. I think as long as you have this stuff well sorted in your head and you have access to these equations, this is actually a pretty straightforward first half of a chapter. Are there any other questions out there?
Yeah, Mr. Robinson, this might be like a dumb question, but how would you like differentiate between a chaotic function and like a sine function if both the points both oscillate?
Oh, that's a really interesting question. So,
The dots don't connect for a series, I guess that's one thing.
yeah, that is true. There is a way, though, that you could define out what it's doing using a sine function, except you would need the amplitude of the sine to grow exponentially. So if you did e to the x multiplied by, let me go to Desmos. If you did e to the x multiplied by sine of x, the peak of the waveform could be used to match up pretty clearly what yeah, so it's this going off to the right. This thing is getting taller and taller and taller and taller, but also oscillating back and forth. So if you only pulled the amplitudes, right, like the peaks here, you could use those peaks to model what a chaotic function is doing. And you'll see that very quickly, like Desmos can't even calculate all of these values. It's not that it doesn't exist here, it's that Desmos doesn't have the resources to calculate this graph moving on into the future, which is, you know, part of what makes this so hard. You have the right intuition though. If you watch that 3 blue, 1 brown video, this is actually the kind of logic that makes the infinite series calculable if you're counting up the counting numbers and you arrive at -1/12. The logic is we find another way to generate 1 + 2 + 3 + 4 and manipulate it, and that's how we can show that the sum is -1/12. It's good intuition. You can use this to generate out a chaotic series and then try and predict where it goes. But even this right here, y is equal to e to the x sine of x, is a really hinky object to try and play with, even if you were to try and do calculus with it.
Oh, okay.
It's a good question. It's a question that's so complicated, like I can't answer it, and a good answer to that question would still be fuzzy. Anyway, any other questions out there before you guys head off to a marathon of AP tests and I head off to a marathon of finals? Okay. If not, I'm going to post that review assignment and, you know, do it at your leisure. It won't be due until next Friday. So just finish your AP stuff first, deal with that, and then deal with it whenever you have time. And best of luck to you on your, what is it, 4 AP tests? For some of y'all, taking all of them?
3.
3? 3, yeah. Best of luck to you on your 3 AP tests. Go out there, bag up that free college credit. and I'll see you guys Thursday after this Thursday. Yeah.
All
All
right.
right. Yes.
Peace, y'all. Take it easy.
See you. Good luck.
Thanks. I might need it for the thing I'm doing on Friday. I have a freaking exit interview with 3 professors. It's an hour-long interview, and I need to impress them.